Size is the most important property because once you understand the trend in size and how you make a prediction about the relative size, it's going to help you understand all the other atomic properties. And the second atomic property we will discuss is ionization energy. It is the energy required to remove one electron from the atom itself to form a cation. Based on that definition, we can have several number of ionization energies. First one corresponding to removing the first electron, second one removing the second electron, third ionization energy removing the third electron. And you can imagine that, of course, removing the first electron is going to require much less energy than the second one. Why?
When we remove the first electron, there's a much greater attraction between the protons and electrons. So that's why I believe it's harder to remove the second electron.
Thank you, that's correct. So if you compare removing an electron from a neutral atom in the first case, it's going to be easier because it feels less attraction. But once you have an ion already and you start removing an electron from an ionic positively charged particle, it's going to be harder because the electron now is feeling much more attraction. When you have more charge on the ion, the electron that you want to remove is going to be feeling more attraction, so it's going to get harder to remove it. It's going to require more energy to overcome that attraction. How about the trend of the ionization energy throughout the periodic table? It's going to be the same argument depending on our understanding for the size. Because when you go through a periodic table from the left to the right, what happens to the size? It gets smaller because the charge on the nucleus is larger, so the size gets smaller, right? So they are in the same energy level, but they feel more attraction and the size gets smaller. So what will happen to the energy needed to overcome that attraction? So as the size goes smaller, the energy will grow larger because you will need to overcome more attraction. The electron is much closer to the nucleus and feels much more attraction. So it's going to be much more difficult to overcome that attraction. So that explains the increasing magnitude of the ionization energy as you go from lithium to all the way to neon. Neon is the most difficult to ionize. And in fact, all the noble gases are extremely difficult to ionize. And that's explaining why they actually don't react in any chemical reaction, because it's completely difficult to ionize them. It requires much, much more energy to ionize them. And that's actually an indirect measure for the stability of the electronic configuration, right? The most stable electronic configuration would require a lot of energy to break or to ionize or get an electron out of. So because noble gases are the most stable electronic configurations throughout the periodic table, they have the highest ionization energies, right? And as we said, as we go from the left of the periodic table to the right of the periodic table, the ionization energy will be increasing because of the decreasing size and the increasing attraction, or the increasing stability of the electronic configuration of each element. But we have two anomalies here. The first one is this one, corresponding to boron, and the second one is this one, corresponding to oxygen. Those are not following the trend. If it followed the trend, it should have been higher than the previous element, right? It should have been increasing, which means it should have been higher than the previous element. Why is it lower? first anomaly between group 2 and group 3. Group 2 will have an electronic configuration with s orbital that is completely filled and p orbital that is empty. That's group 2. In comparison to group 3, which will have s orbital that is completely filled with the p orbital that has 1 electron. What happens when you remove an electron from group 2? You will basically break the stability of the completely filled s orbital. And as we learned in the previous lecture, completely filled orbitals are extra stable. So they have much lower energy. So when you make a change that will break that stability, it will require a lot of energy to overcome that stability. So it's going to be much harder to remove an electron from here and overcome the extra stability of the filled orbital. What about the second case? You're removing an electron from a p orbital. Once you remove it, the p orbital will be completely empty and the s orbital will still stay filled. So you're actually moving from an unstable configuration to a more stable configuration with a completely filled s orbital and a completely empty p orbital. Okay, that explains why it's easier to remove the electron in this case in comparison to the electron in that case, which will be much harder. If you understood this, you should be able to explain the second anomaly between group 5 and 6.
Is it because in group 5 you have half of the p orbital filled, and in 6 you start up again, like you fill across an orbital?
Okay, so let's draw the electronic configuration of 5 versus 6, and so that people can see what you're talking about. In 5, you will have a completely filled s orbital and half filled p orbital, right? In 6, you will have a completely filled s orbital and a partially filled p orbital. So now you're comparing removing this electron in comparison to removing this one. Which one is going to be easier?
The second option?
The second one, because you're actually, when you remove this electron here, you're actually moving from a partially filled orbital to half-filled orbital. And as we learned before, half-filled orbital is more stable. So it's going to be a favorable change here. So it's going to be easier to remove this one. A favorable change, easier, so lower ionization energy. In the other case, you're actually, if you try to remove this electron, you're actually losing the extra stability of an already half-filled orbital. So that is going to be unfavorable, hard change to take place. So that will make the ionization energy higher. Okay, thank you. We learned that the size increases as you go from the right to the left downward because the attraction decreases as you go from the right to the left downward. Okay, and ionization energy is going to be the other direction. So it's going to be increasing from the down left hand side of the periodic table up to the right. So it's in the opposite trend in comparison to the size. As I said, the most important one to understand and memorize is the trend of the size. Once you know it, you should be able to make predictions about all the other properties, because as we will learn later, all the other properties will have the opposite trend to the size, and we'll understand why as we discuss each one of them. Okay, So the third property is electron affinity, which is basically the energy needed to gain an extra electron rather than lose an electron. So it's opposite to ionization energy. So it's actually a measure for the tendency to form an anion. Okay, it could be thought of as the opposite process. If you take an anion of that element and try to remove the electron, how much energy you will get, how much energy will be released. So if the ionization, the electron affinity is larger negative number, that means a lot of energy is released, which means the atom actually favors adding an electron, okay, to form an anion. So which group of elements will have the most negative electron affinities and why? Which one you expect will have more favorability to add an extra electron? Is it gonna be the right-hand side of the periodic table or the left-hand side of the periodic table? The larger atoms or the smaller atoms? The small atom is small because it felt more attraction to the nucleus. So that means that the nuclear charge is strong enough to pull the valence electrons closer to itself. If it's strong enough to do so, it's gonna be strong enough to add an extra electron. It's gonna favor adding an extra electron.
Sir, do you mean smaller in radius?
Smaller in radius, smaller
Okay.
in size, yes.
All right.
But
thank you.
if you're talking about a large atom, the large atom, the nuclear charge is much weak or much small, which makes the attraction weak. If it's weak, attracting the electrons that it already have is gonna be even weaker, attracting an extra electron from outside. So electron affinity is gonna again go in the opposite direction to the size. Smaller atoms will have higher electron affinity, larger atoms will have lower electron affinity. It's actually basically the same trend for ionization energy. Smaller atoms had larger ionization energies, larger atoms had smaller ionization energies. So it's basically, as we said, it is the same trend. And that will make group 7 or group 17, sometimes in the periodic table it's going to be called 17, halogens are going to be the most electron affinity elements in the periodic table, the elements with the highest electron affinity overall. Anything else away from the most right-hand side of the periodic table is going to have much smaller electron affinities, okay? So electron affinity is going to go in the opposite direction to the size, as we understood, or as we discussed in the previous slide. But we will have a couple of anomalies as well. And that is going to be explained in the same way we explained the anomalies in the ionization energies. Because it is all about the relative stability of the electronic configuration before and after making the change that you make, which in this case is adding an electron rather than removing the electron. So, for example, the electron affinity of group 1 versus 2, adding an electron to group 1 is going to be much more easier than adding an electron to group 2. Because adding an electron to group 1 right here is going to make the ion have the stability of a completely filled s orbital, right? Which is much more stable. So it's going to be a favorable change. So it's going to be an easier change to happen. But if you try to do the same thing for group 2, you're actually adding an electron to an empty orbital. So you are breaking the stability of a completely filled s orbital to a less stable configuration. It's not going to be a favorable change to happen. It's going to be hard to happen. It's going to be hard to add that electron, which means the affinity is going to be smaller. Same thing is going to happen if you compare group 4 to group 5. You add an electron to group 4, you're actually moving from a partially filled p orbital to half-filled p orbital, which is more stable, less energetic. So that's going to be higher electron affinity for this change to happen. But if you try to add an electron to an already half-filled p orbital, you're losing the stability of that half-filled p orbital. It's a harder change to happen. It's going to be less affinity corresponding to that change. Last one is the electronegativity, which is basically the relative attraction of the atom to electrons in a chemical bond. So it's not just for the single atom. It is when you have atom A in comparison to atom B, and you have an electron that forms a bond between them. How stronger A will pull this electron in comparison to B. Okay? And it's actually not an experimentally measured property. It's not something like size that you can measure experimentally, or ionization energy that you also can measure experimentally. It's something that we calculated based on the 3 previous atomic properties. It depends on the size, the electron affinity, and the ionization energy. And the relationship is straightforward. When you have higher electron affinity, it's gonna translate to higher electronegativity, right? Higher electron affinity in the first place was a result of the stronger attraction of the nucleus to an extra electron from outside. So if the nucleus in this case is strong, have a larger charge, and can attract electrons stronger, is going to mean that it has higher electronegativity. Lower ionization energy translates to lower electronegativity. Same thing. Lower ionization energy means the attraction of the nucleus is weak, and it's easy to overcome it to remove an electron that already belongs to that atom. If the attraction is weak, it means it's going to be pulling the bonding electrons much weaker than any other atom. So that will translate to a lower electronegativity. Higher electronegativity value means that the atom will be attracting the bonding electron much stronger than the other atoms. So it will have the electron closer to itself, or have an extra electron density on itself inside the molecule. Based on these relationships between electronegativity and ionization energy and electron affinity, you will find that electronegativity is basically following the same trend as both of them. It's going to increase as you go from down the group upward to the right-hand side of the periodic table. So the highest electronegative atoms will be on that top corner right here. The lowest electronegative atoms will be this corner right here. We already discussed all atomic properties, and what we will do next is gonna be trying to explain the macroscopic properties, the bonding, and the reactions in light of these atomic properties. These atomic properties are not just abstract ideas. They're very useful to explain why each element react in the way it does. So that is going to be the topic for chapter 7.